So what we're going to consider now is volumetric analysis and the primary standard. Volumetric analysis just means that we're going to use volumes to determine quantities. And a common way that we do that is with a titration reaction. A very common titration reaction is an acid plus a base reaction. What's the reaction type then? What do we call that?
Neutralization.
Yeah, so a neutralization. And we know that we used phenolphthalein indicator for our previous titrations, so for those of you who did the titration competition. And you know it changes colour to indicate that this neutralization reaction has occurred. Do you remember what colour phenolphthalein is? Pink in
Base.
and base, and
Clear.
colourless in an acid. That's right. So for our prac that we're going to be doing very soon, we're going to use hydrochloric acid and sodium hydroxide. That's going to be our reaction. We know then that produces a salt and water, so it's sodium chloride and water. And what we're going to do is, this will be our unknown. The concentration of the hydrochloric acid is our unknown. So in order to find that in any titration, remember we're titrating a known quantity against an unknown. So that means that we have to know this one, don't we? Well, the problem with sodium hydroxide is it's not stable. It's hygroscopic. Well, we'll talk about sodium hydroxide as solvent. It means that it absorbs moisture from the atmosphere.
Isn't that what's in your pencil cases and stuff?
No, silica gel. No, it's not this, because this is a bit too dangerous to put in there. It also will react with carbon dioxide in the atmosphere. So that means that, and I've got you some sodium hydroxide pellets here. And I've given you all a piece of paper towel for your desk so that you can just have a look and see what happens. Now, we know it's highly corrosive, and if you rub it in your eye, you'll be permanently blind because it causes the cornea to go cloudy. So don't do that. Just going to be looking at them.
Poke it.
Doing
Twist it.
Feed it. I think there's more than 3 there. Twist it. What are you going to put on?
I don't see anything.
Probably not.
Yeah, but like, is it happening?
That would be
Something
massive.
What if you have flask?
You'd be dead.
Yeah, you'd be dead.
You'd be high.
You'd be high, you'd be going up in the head.
Alright, so we're just going to leave them sit there and do their thing while we go on further.
It's getting wet.
So, why is this going to be a problem?
Because there's
less moisture in the atmosphere.
Change the amount of reactor.
Yeah, because if I measure out 2 grams of sodium hydroxide, how much of it is actually sodium hydroxide? How much of it has already reacted with the carbon dioxide and is no longer sodium hydroxide, and how much of it's actually water? I don't know. And so we can't just do this titration as it stands, like this. What we need is another step, and that is something that we can titrate against the sodium hydroxide to standardise that solution. And this is why we need a primary standard. So the primary is the one that we start with. And a primary standard needs to be unreactive with the atmosphere and water. Hopefully it is inexpensive, because we all know that scientists are poor. We want it to be available in high purity, and so it's not going to be contaminated with other things. Here's a hard one for you. Well, maybe a hard one. We want it to have a high molar mass. Why?
So we can measure.
We can measure things with a low molar mass.
You give it more precise. Make it more precise.
How?
If it's a bigger molar mass, that means a smaller amount will be a smaller piece.
Number of moles.
Yeah. So if you have if you have 500 mils or 500 grams of something with a molar mass that's 1,000 grams, it's 0.5. And if it was 500 grams of something of 500 grams, it'd be 1. So it's closer. I don't know.
Is it because it's less reactive?
No, we can't. The molar mass and reactivity can be, won't necessarily have any relationship to each other. But it is to do with how precise your measurements can be, yes. We also want it to be soluble, but really I think if that's really a given, don't you think? That why would you be choosing a compound that's insoluble as your primary standard? This one doesn't really give me much information about your understanding of primary standard. So even though it's true, I wouldn't pay you very many marks for if that was your answer. I would rather you be focusing in on, even this one, yes, it's true and it's important, but the really critical factor is whether it's unreactive with the water in the atmosphere. And so, if you look at the Prac that we're going to do, you can see that we're going to be starting out with making up a solution of our primary standard. So if you want to pull out your Prac, okay, this one here. See, sodium carbonate. Which compares quite favourably too, doesn't it, with sodium hydroxide as far as the molar mass is concerned. This one's going to have a much higher molar mass than this one anyway. But we can't use this one because it's just not suitable. If you have a look at your little lumps of sodium hydroxide on your desk, how do they look now?
Moist.
They look wet, shiny. Yep. So they haven't been out very long, and they're obviously taking in moisture from the atmosphere. The longer we leave them, they'll eventually melt. So your first task will be to make up your primary standard solution, and our gear is just in the tubs in the back corner over there next to the pass-through. You want to make sure, does everyone remember titrating? Did people titrate last year?
Yeah. Kept on
Yeah.
overshooting.
Well, that's a common thing to do. Your glassware must be clean, so you should rinse your glassware 3 times. When you're rinsing, a small amount of liquid, okay, you don't fill it up because you can't agitate if it's full. You only want a small amount that you can really vigorously move around, and you do it 3 times to make sure that you have got rid of any contamination that's inside the glassware. If you are going to dissolve the sodium carbonate in a beaker, you must make sure that you rinse the beaker well into your volumetric flask. And I'll just grab a volumetric flask because unless you did the titration competition, you didn't use.
Sorry, I can't use it yet.
So what we're interested in is filling to the etched line on the neck of the volumetric flask. Okay, this is a 200 ml volumetric flask, and it only measures 1 volume, and that's it there. When you're picking out your volumetric flask, grab a stopper as well, and they're different sized necks on the flask, so make sure that the stopper goes with the flask you've got, because when you stick that in and you start shaking it, it's not going to work so well if it doesn't fit. For today's, we just want to probably fill it to about just underneath the fill line, and make sure your sodium carbonate's fully dissolved. If you transfer the sodium carbonate directly into the volumetric flask, only put a small amount of water in and shake until it's dissolved, okay? Because if you put too much water in, you won't be able to agitate it enough to dissolve the compound in there. You're going to need to label your solution for your pair for ready for titrating on Wednesday, and just we can put them on the shelves at the back there. Does anybody? It's not hazardous as well. I mean, that's a good thing too. The sodium hydroxide is certainly much more hazardous than the sodium carbonate, although it's very good for cleaning.